All right, let's get started. Just so everybody's aware, when it comes to homework, we have a homework due next Friday. I actually don't think I'm going to push this one back because after today, and definitely after Monday, you'll be equipped to handle everything on that homework assignment, so I don't really think there's a need to push it back. Other than that, are there any other big ticket questions? Because I'd like to just sort of jump right into it. Am I good?
Are you sure you're not pushing it back?
I am sure. I know you're looking out for me, though, right?
Yeah. No, I got all for you.
No, you have my back, that's for sure.
I'm going to give you a call and ask what you trace you.
Okay. All right, okay. Funny times. All right. So let's sort of recap where we left off. So last time, I think we finalized a sort of a formal expression for net area. So keep in mind, let's just sort of make sure where we're at. So we're talking about tension members. We're talking about applying axial tension to a member and determining its axial capacity. Now it's a function really of two things. The material properties, which are really easy lookups, but then there's the section properties, which is what we're on now. So we have gross area and net area, and I think after last time, I think you have a pretty good general idea of what's going on with net area. In general, it's the gross area minus the area lost due to bolt holes. Again, the diameter of the hole times the thickness, not pi d squared over 4. But then we add any necessary stagger factors. Okay, so that's for bolted connections. For welded connections, net area equals the gross area. So, how's it going? Hey. What's up? Hey. You good? You good? See, now remember, this is what happens. Remember what I said? You come in 2 minutes late, and you're like, oh, excuse me, sorry, excuse me, what's up? Oh, so pardon, excuse me. Oh, goodness. All right. So we talked about last time how to compute the net area for a parallel bolt path, a grid-like arrangement, and then for a staggered bolt path. And this is the one that we left off last time. Does anybody have any questions on that one? Now, one of the things about this problem is that the stagger factors were the same, okay? So what about a situation where the stagger factors are not the same, okay? And that's going to be this one. So this one, we have a situation where we actually have a stagger path occurring across the angle, across the leg. So how do we analyze this, and how do we determine the net area? To be fair, this one is a little bit of a challenging one, and I'm doing this just so you can get a little bit more of an understanding in terms of geometry and how things are going on. So just like I said, this one's challenging. So don't worry if you look at it and you go, huh, what? Now, remember, 3/4 inches diameter bolts are used. So what does that mean in terms of the hole diameter? 7/8 inch hole diameter. Okay, now we have a member that is comprised of an L 7 by 4 by 5/8. So that means that the thickness of the legs is 5/8 of an inch, and the angle has 2 legs of differing lengths. So when you specify angles, you specify the longer leg first. So this is an angle with a 7-inch long leg this way, a 4-inch long leg this way, and each of those legs are 5/8 inches thick. Now, everybody okay on that? Now, what is the first step in computing net area? That should be, at this point, should be a given. Whenever you need to compute net area, what's the first thing you need? Gross area. What is the gross area of an L 7 by 4 by 5/8? There we go. You got to open up the manual and look. remember, I've got this drawn with nice little pretty angles, like right angles, but really that's not the case. If you've ever seen a piece of angle iron, you know, the ends are rounded, so it's not as simple as just, you know, computing the area of the equivalent plate, although it'll get you pretty close. Really, you just need to look that up. All right. You said the right answer because I heard you. That was correct. But I heard a question. What?
Yeah, what were you looking for?
Will you tell me? What am I looking for?
I don't know. Something about the gross area, net area?
Well, what are we doing? You tell me. What's the first step in computing the net area? Well, good. Well, what is it? What is the gross area of an L7 by 4 by 5/8? Say it again. 6.5 square inches. Now, what page are you on? 1-44. Okay, so I want to make sure that everybody is able to find that value. So we're in a different table now. So is everybody able to find it? If you're not, raise your hand. This is not. Don't be Paris. This is what we're here for, so that everybody's able to find these quantities. 7 inches, 4. I'm looking at it that way. Yeah, so this is the long leg, and that's the leg sticking out. Yep. These two right here. Yes. Is everybody able to find the 6.5? Everybody good? Okay. Hold on. Okay. Okay, so need that. So we know that AG is 6.5 square inches, and we know that the thickness is 5/8 of an inch. Okay, so right off the bat, everybody should be comfortable with that. Now we also know that the bolt for the bolts, we know that the diameter of a bolt, excuse me, is 3/4 of an inch. So the diameter of a hole is what? 7/8. So therefore, the area of a hole, we'll go ahead and compute that now, is the diameter of the hole times the thickness. And so that equals what? We'll say to, I don't know, 3 decimal places. 547. Do I have a second on that? Everybody okay on that? Okay. Now, the problem is this. Does everybody notice how, you know, if I start looking at net areas, so first off, right off the bat, looking at this problem, is the net area, or the lead line, is the lead line going to be the bolts on the left side of the connection or the right side of the connection? Say it again. The right, because the main body of the member is all the way over here, so really we're talking about these. Okay? Now, if you look at that lead line, does everybody see how we have a stagger that occurs across the leg? Does everybody see that? Everybody see that? Now, for each of these, we have, so for each of these paths, we're going to have a stagger factor, right? Now, this 2 inches, bless you, this 2 inches is going to be that distance right there. Is that going to be the S value or the G value? What's the difference? There. One is parallel to the stress, one's perpendicular to the stress. Okay, so the stress, I don't know what happened there. The stress is acting along the angle. So this dimension right here is going to be what? S. Okay? But does everybody see how each of these is going to have a different G value? Right? Because we're going to have basically a staggered path here, and we're going to have a staggered path there. Oh, backwards. We're going to have a staggered path here. We're going to have a staggered path here. So we're going to have different G values, and we're going to have to compute those accordingly. Now, in order to compute these G values, I'm going to pull a little trick. Okay? This is what I'm going to do. All right. In order to look at this plate a little more effectively, this is what I'm going to do. I'm going to break out my samurai sword or lightsaber if you're a sci-fi fan, and I'm going to make a cut right there. Okay? Everybody see that? I'm going to cut this right here. Then what I'm going to do is I'm going to take this piece of angle right here, and I am going to stack it on top of there. And I'm going to turn this into an equivalent plate. Okay? Everybody okay with that? So before I do that, let's look at some dimensions. Okay? Now, what is this dimension right here? 7 inches. What is this dimension right here? 4 inches. Now, what is this dimension right here? 4 minus 5/8. Everybody see that? It's 4 minus a thickness. Everybody okay with that? Okay. So I propose then that this is what? 3 3/8? So if that is 3 3/8, let's take a look at this down here. So samurai sword or lightsaber, and then take this, stack it on top. How tall is the entire plate? It's 10. It's not 11. It's 10 3/8. Does that make sense? All right. There we go. This is 7, right? This is 3 3/8. So stack. It's not 11. It's 10 3/8. Everybody okay with that? So here is the plate. All right? And then there's a line somewhere about, like right there, that's where we cut it. All right? So we got, bolt hole number 1, bolt hole number 2, bolt hole number 3. And what dimensions do we know? Okay? Well, let's see. What's this dimension right here? That's 1.5 inches, right? What is this dimension right here? 3 inches. What's this dimension right here? 1.5. And how tall did we say the whole thing was? So, what's this? And what is 10 minus all that? So it's 10 minus 6. So what? 4 3/8? Did I do that right? So if I'm looking at the plate this way, right, here's what it's going to look like. Right? And so I'm going to have then 2 failure paths that I need to consider, right? I'm going to have this one, and I'm going to have that one. That second one, I subtract 3 bolt holes, right? How many stagger factors do I add? But, what's the deal? They're not the same, right? It's not the same stagger factor. It's not like the last example where we would add 2 stagger factors, but it was the same diagonal path, right? See, this path here, so we have this, and then we have this, right? Both of these have, what did we say? Was it an S of 2 inches? Did we say this is S is 2 inches? But this one and this one have different G values. So this one is what? 4 3/8. And that one's 3. What do we think? Are there any questions? No. Tell you what, you can skip it on the exam. Now, how that affects your grade is entirely up to you. Are there any questions? Seriously, though, are there any questions?
Like on that bottom, is that, are we like flattening out like the italic, we're taking an L and making that so the whole thing's flat?
Yes.
So we're not having to worry about what we might like
Basically. But the real reason for flattening it is so we knew what that gauge distance was. So we knew that that was 4 3/8. I understand this one is challenging. So here's what I propose. I propose that we have 2 net area paths that we need to consider. So if you want to throw some names in, like an A, B, C, D, and E, I propose that there are 2 paths that you need to consider. We have A, B, D, E. And what's the formula going to be for that? The net area is going to equal the gross area minus what? 2 bolt holes, right? And so what does that come out to be? I'm just curious. 5.406. So we'll say 5.41. And then what about the second one? The second path is going to be A, B, C, D, E. Okay? And so what's the formula for that path going to be? Well, it's going to be the gross area minus 3 bolt holes plus what? Now, is it 2 stagger factors, or do I have to add each stagger factor separately? I have to add them each separately. So we're going to have S squared T over 4G1 plus S squared T over 4G2. Say it again. 5.21. Do I have a second on that? Did I go through that too fast, or do we need to plug and chug? What's the gross area in each of these? 6.5. What's the area of the hole? It's 0.547. What's S for each of these? 2 inches. We know the thickness is 5/8. G1 and G2 we've got right here. So it's just plug and chug. Are there any questions? So what is the net area? Is it this one or that one? Like the bigger one or the smaller one? Smaller one. So 5.21, yes. Stagger factor. It's for, we add one for every diagonal path. So because there's two diagonal paths, there's two of them. All right. Are there any questions? I got some puzzled looks on everybody's face. So, like,
What's the most stagger factor for the reason we have
look at your homework. Where you? There are a few.
I'll get back to you on that.
On the homework? No. Guys, do we have, I mean, if you got questions, please, I mean. All right, hold on. Y'all need to pay attention. All right, so he said, why do we select the smaller area? If I'm yanking on this member, what's the path of least resistance? This path offers the least amount of steel to resist that load. So if I yank on it, it's going to fail through this path before it fails through this one. Okay, these are good questions. Okay, and if you got a question, please, you're not going to, don't be embarrassed. I mean, please ask. So, y'all good? That is why, because there are no diagonal paths along ABDE.
Okay, so G doesn't matter if it's straight.
Exactly. Yes. Or basically, if it was straight, S would be 0, so it would all cancel.
Oh, okay.
See, like, this is like the theoretical, like, the smaller, it's going to have this path of least resistance, but in a practical sense, is this always the case?
Yeah.
Like,
Well, keep in mind that all of the little uncertainties are taken into account through things like loads and resistance factors. So what we're doing is we're using some mechanics to compute these quantities, but we take our uncertainties into account with our phi values and load factors and things like that. Everybody good? All right. Now, okay. Now let me be clear on something. I'm gonna skip ahead a little, or skip behind a little bit. Remember what we're doing, okay? We're looking at limit states, okay? We're trying to define conditions upon which we define that the member has basically reached failure. Now this is gonna be a little bit like movie times, but I want everybody to sort of pay attention. Okay, so remember, we have a tension member, we're yanking on it, okay? Now up until now, we've been looking at two limit states. We've been looking at yielding in the gross section and fracture in the net section. So in order to compute those capacities, we need to be able to compute gross and net areas. I think by now I think we're good, because I've pretty much beaten gross and net areas into the ground, okay? But what we have is another situation that we need to consider. Okay, if you recall, I presented a formula for the capacity for fracture in the net section, and it's not the limiting stress times the net area, it's the limiting stress times the effective net area. So I kind of want to explain what's going on with that, okay? So this is going to be a little bit like movie time, but I want everybody to sort of follow along with me. Okay. Now, typically when we have a tension member, we don't connect all of the cross-sectional components. So by all the cross-sectional components, I mean take a look at this, okay? We have an I-beam or a wide flange, and we have the flanges connected, but not the web. Okay, does everybody see that? That's very common to not connect every component, okay? Usually it goes along with how the structure is connected and how that fits into the geometry of the associated members, okay? But ultimately, that connection scenario and how you transfer load affects how the connection performs, okay? What I have here on this image is a screen capture of a finite element analysis. This is looking at a T-shape being subjected to tension. And what you're looking at is what's called a stress contour. Okay? So you run this highly detailed, three-dimensional computer model looking at stresses, in 3 dimensions. For those of you in structural analysis, this is basically doing what RISA does, but amping it up to the extreme. 3-dimension, shell elements, whole 9 yards. Now, what you're seeing is the propagation of stresses as you apply tension on this member. And it looks nuts. It's all over the place, right? Looks like a weather map, okay? Now, here's the point, okay? If you look here at the bottom, like right here and right here, this is the gross section. And notice how down here, it's all the same color, like it's all yellow. Because down here, the stresses are fairly uniform. They're fairly consistent. See, out in yielding in the gross section, we didn't have to consider this effective area issue. We didn't have to consider that for yielding in the gross section. But we're not looking at yielding in the gross section right now. We're looking at fracture in the net section. The facts are we have to account for that. We have to account for the fact that there is a non-uniform stress distribution right there around the connection. See, the facts are right there at the connection, not all of that net area is effective in transferring stress to the member, okay? Because the stresses are going all over the place. This is very complicated math. This is very complex phenomenon, okay? We have a name for that phenomenon. The idea that some of the components of the cross-section are lagging behind and they're not, it takes a while for them to quote-unquote catch up and receive the stress that the connection is being applied to. We have a name for that phenomenon. We call it shear lag, okay? So shear lag is the name for that phenomenon of the stresses being non-uniform right there around the connection. We have to determine how much of that net area is effective in transferring stress, okay? Like I said, this is not easy to do. Fortunately, the code makes it a little easier for us through the use of some nice empirical equations. So I want everybody to open up their manuals that they all brought with them. That they all brought with them. That they all brought with them.
Would that only be where the holes are in steel?
We are talking about where the connection is. So we're on 16.1-30. What do I have here on this slide beyond just an image of what's in the code? Look at me. Look at my manual. I have a nice little tab called U right here. You will be referring to this table quite a bit on your homeworks, on your celebrations of learning. So, well, the shear lag factor is called U. So you need to tab this one for sure. Now, is everybody here? Everybody able to find it? Were you able to find it? Were you able to find it?
I'll find it on my kitchen.
Next to the F flat. So. Everybody able to find it? Okay. Somebody do me a favor and read out case number 1. Hold on. I'm going to call on you. Read out case number 1.
All tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds.
There we go. Okay. And what is the U value in that case? 1. Okay. So let me explain what that means. Okay, so case 1 would be a scenario where all of the cross-sectional elements are connected. So if we're talking about a wide flange, that's every flange, all the web, every component is connected. And what the code is saying is that if you are transmitting the load directly to all of the cross-sectional elements, we don't really need to worry about shear lag from a design standpoint, and so we can take U to equal 1. Okay? Now, let's read case number 2. Somebody else read case number 2. How about you read case number 2? Here, you right here. Here you go. Because you were ready with your manual. You had it all prepped up, ready to go. And so you could stop at the end of the sentence.
All tension members except HSS, where the tension load is transmitted to some, but not all the cross-sectional elements by fasteners or by longitudinal welds in combination with transverse welds.
Okay, all right. So case number 2, so case number 1 is saying if all of the elements are connected, U is 1. And case number 2 is saying if some of the elements are connected, here's our formula. And it says 1 minus X bar over L. We're going to talk about what each of those mean here in a second. All right. Now, a couple things. It gives you some caveats. It says all tension members except HSS. HSS stands for hollow structural shapes or hollow structural steel. Basically, we're talking about tubes, like rectangular square tubes. So we don't have to worry about that here. Another thing, if you follow the next sentence, it says alternatively, case 7 is permitted for I shapes and case 8 is permitted for angles. So right off the bat, when you're performing shear, when you're computing shear lag factors, multiple cases may apply. So you kind of have to go through the entire table and figure out which one applies for your cross section. So you kind of need to take some time and review this to make sure that you're okay with what's going on. Now, the question might be what's going on with X bar and what's going on with L? What are these? Let's take some time. So one of these cases, so case 2, is primarily the one that you're going to be using for just about any problem, any tension member problem, period. Not just in this course, but in practice. Okay, so U for case 2 is 1 minus X bar over L. Now, I like to write it like this, 1 minus X bar sub CON divided by L sub COM, because I want to describe what those terms mean. Okay? So we have an X bar and an L. X bar is what I like to call the connection eccentricity, whereas the L is the connection length. So I want to make sure that it's clear that these are referring to parameters related to the connection. Okay? Now, specifically, X bar is defined as the distance from the connected face to the centroid. Okay? The connected face to the centroid. Okay? And I want you to be absolutely clear about that, because if I give you a, let's say, a channel, you know, do you look up the X bar? Do you look up the Y bar? It depends on the problem that you're looking at. Okay? So you need to be clear. The L is the connection length. Let's take each of these one at a time. Let's start about connection eccentricity. Okay? So for most cases, you simply look up the appropriate, keep in mind, appropriate centroid value. Okay? So let's say it's a channel. Let's say you have a channel. Let's say here on the bottom, we have a channel connected via the web. Okay? It's a very common connection scenario. The X bar value is the distance from the connected face here at the back to the centroid. Okay? Now for channels, if you look up channel properties, that is X bar. Okay? So you would report the X bar value, and that's going to be what you use in this equation. For angles, it depends on which face of the angle is connected. If it's the long leg, use the X bar. If it's the short leg, use the Y bar. Okay? It just depends. Okay? How do you know which value to use? Remember, if you go to table 1-5 or 1-7 or what have you, there's a nice little pretty image up here that tells you what these values represent. So make sure that you're going off of that accordingly. Everybody okay so far? Now, I got a special case for you. If you have a wide flange that is connected via the flanges, this is a very special case. Okay? If you have a wide flange that's connected via the flanges, the way that you get your connection eccentricity is you look up the Y bar for an equivalent WT. Okay, so what do I mean by equivalent WT? Well, let's say you have a W12 by 30. An equivalent W30 means taking your samurai sword or lightsaber and chopping this thing in half. So if you chop that thing in half, what does that mean? Well, its depth gets cut in half and its weight gets cut in half. So the connection eccentricity for a W12 by 30 would be the Y bar for a WT 6 by 15. Okay? And there is a corresponding WT for every W section in the manual. Hence, that's one of the reasons that I have my WT shapes tabbed. Okay? Because we're going to use that pretty relevantly, or pretty regularly. Keep in mind, remember, we're talking about empirical expressions. We're talking about provisions that are designed to be simple to use, but match the test data as closely as possible. Okay?
So that means we don't have to calculate the centroid, right?
That's what the WT's tables are doing. So when you look up the Y bar for a WT, that is the centroid from this connected face to here. That's what Y bar is. Yeah. Everybody okay with this? Now, hold on for a second. Let me see something. One thing I will mention, I'm actually, before we move on, I want everybody to turn to the WT shapes.
Since the example is the 12 by 30, since there's no WT 12 by 30, we're going to do WT 6 by 15, or now do we like multiply like?
No, you don't change the value there at all.
Okay, we're not going to multiply by 2 because it's
No. You just use the value accordingly. Okay, I want everybody to pay attention to this. This is important. Is everybody at a WT table? Table 1-8, any one of them. Now, look over here on the right page. Let's say the XX axis. Now, you notice how there's two Y distances? Y'all see that? What are the two Y distances? There's a Y bar and a Y what? YP. Does everybody see that? All right. If you use the YP right now, bad. Don't use the YP. The YP quantity is related to bending, okay? Specifically, it's the location of what's called the plastic neutral axis. You don't understand what that means yet? You will, okay? We'll talk about bending and plastic neutral axes probably in the March-April timeframe. But for now, I want you to be crystal clear. Avoid those for now. You'll understand what they mean later, but just don't worry about them now. Everybody okay? Okay, so that's X bar in a nutshell, okay? What about the connection length? What about L sub CON? The connection length, first off, I want you to understand why it affects the shear lag factor. So what I have here is just sort of a conceptual layout. As the connection gets longer, what happens is the stress, it's got more room to propagate along the section. So you can kind of see from here to here, from the top to the bottom, as the connection gets longer, more of that section becomes effective in transferring stress, right? So look at the equation, 1 minus X bar over L. As the L value gets larger, that shear lag factor is going to go what? It's going to get larger or smaller? If the L value gets larger, what happens to U? It gets larger as well, right? 1 minus X bar over L, if L gets bigger, U gets bigger, right? And that reflects what's actually going on. The connection length gets longer. You got more of that section effective. Now, how do you compute that? It's the out-to-out distance between your bolt holes. So if you have a staggered connection, the farthest bolt this way, that's your connection length, okay? So that everybody's clear on how to compute that quantity. It's center-to-center bolt spacing. Yes?
So why don't you, do you not have to consider the bolt spacing itself?
Let me say this. You are getting a little ahead of yourself. We are going to have a whole to-do on the actual layout of the connection itself and on the capacity of the bolts, how far apart the bolts should be spaced from each other, how far apart the bolts should be spaced from the edge of the plate, slip critical connections. That's going to be out. Don't worry. we will get there. Right now, all we're looking at is the tension member as just one whole unit. We're going to get into laying out the connection itself later. Don't worry. We will get there. Any questions? So if you have a welded connection, the connection length is taken as the out-to-out length. If you have a connection like over here on the right, which is what's called a balanced connection, we'll do balanced weld connection design later, you take the average of those lengths to determine your connection length. So that would be your L sub CON in this scenario. However, there's also some additional shear lag factors that account for these types of connections specifically. So, all right. Any questions? Now, I want to talk about slenderness. Okay, I want everybody to turn to 16.128, which is the table right next to the shear lag table. Or it's the page right before that. Sorry, page right before that. So we need to discuss service limits for tension members. Up until now, we've been talking about strength limits. It's on 16.1-28. I do that. Sorry. One of the most important service limits that we consider for tension members is a slenderness limit. Now, do we actually have a slenderness limit that we actually have to apply? No. If you read section D1, slenderness limits, there is no maximum slenderness limit for a member in tension. Okay? However, that doesn't mean that you shouldn't employ one for practical purposes. Now, the code specifies that your slenderness should be less than 300. Now, first off, what is slenderness? Slenderness is defined as L over R, okay? The length of the member divided by the radius of gyration, okay? Now, first off, why? Like, what are we talking about? What is slenderness? Why do we care? Okay? Slenderness is just that. It is a dimensionless quantity which measures how slender an element is. So, for instance, this pen is going to have a much higher slenderness value than, let's say, this coffee cup, okay? So why do we care? Well, in tension, slenderness doesn't really affect capacity, but it does affect handling, okay? If you have a piece of steel that is super, super slender, it is really hard to handle. It's hard to pick up. It has about as much stiffness as a piece of wet spaghetti. So you can have damage during shipping. You can have damage during erection. If you have an element that's very, very slender, you can lead to a structure that has excessive sag, excessive vibrations. It can deflect too much under its own weight. So just so you're aware, we don't have to worry about slenderness for tension members, but we should. So we in this course, and I would argue in practice, you should be employing a slenderness limit for tension members just because it's going to make erection of the structure a lot easier to handle. Now, later on, we're going to talk about threaded rod design. Threaded rods are designed to be inherently slender, so we really don't need to worry about slenderness limits for them, but we'll discuss that later. Now, in terms of the math, like I said, slenderness is a dimensionless quantity, okay? Now, the way that you compute slenderness is you take the length of the member and you divide it by the radius of gyration, okay? All right. Now, first off, with the member length, pay attention to the units, okay? I cannot stress this enough. Pay attention to the units. Member lengths tend to be in feet, but radii of gyration tend to be expressed in inches, okay? So if you have a member that's 20 foot long and you have a radius of gyration that's 2.5 inches, you take 20 divided by 2.5, it's going to be wrong, okay? You have to convert your member length to inches, okay? You have to convert that to inches so that the dimension, or so that the computation comes out unitless, okay? Now keep in mind, L over R less than or equal to 300, that's a pretty loose, that's a pretty loose limit. That's really not that hard to assess, okay? Now let's talk about the radii of gyration. Okay, the radius of gyration, does anybody remember how you compute that from mechanics? All right, so the radius of gyration is computed, all it is it's the square root of I over A, That's all it is. It's the square root of the moment of inertia divided by the area. Now don't worry, if you open up, let's say the W shapes, radii of gyration are always there. Look at the W shapes. Let's everybody look at the W shapes. So if you look at the W shapes, you will see, if you look over here on the right page, you'll see where it says axis XX and axis YY? Everybody see that? For each of those quantities, there's an Rx and there's an Ry, okay? Now, when you compute slenderness quantities for tension members, you always use the minimum radius of gyration. Now, most cases, that's the Y, okay? For most cases, that's the Y. So, for instance, look at any W shape, any one of them. Pick any random one, and look at Rx and look at Ry. And I guarantee you Ry will always be smaller, every time, okay? That's because Ry represents the weak axis. So, and one way of describing, well, what's the weak axis? It's the one with the smaller r, okay? That's for W shapes. However, for angles, now I want you to turn to angles. Bless you. Turn to table 1-7. Let's look at an angle. Does anybody see something different on the angle tables? Like there's an x-axis, there's a y-axis, there's a z-axis. What's going on with that z-axis? The z-axis is the, all right, hold on. The z-axis is the principal axis. Remember that whole Moore circle thing? Oh, yeah. The z-axis is the worst case slenderness direction for angles. So for angles, you're going to use the minimum r with respect to the z-axis. So if you look at the z-axis, there's an r value associated with that. But for W shapes, you're going to use ry. If you're ever in doubt, just pull them all and use the smallest one. Okay? So everybody okay with this? Well, you better be. Any questions? What I have here, starting at slide 114 to 115, is a nice little summary for you. These are the summary equations for gross section yielding and net section fracture. So what do we have for gross section yielding? We have 0.9 Fy times the gross area. For net section fracture, we have 0.75 times Fu times the net area times U. So how do you compute the net area? Here you go. The diameter of the hole is the diameter of the bolt plus 1/8 of an inch. Here's your formula for net area. Here's your shear lag factor for case 2, and there's your slenderness limit. Now we're going to add to this list later when we add like block shear and design expressions and threaded rod design, but this is the first chunk of tension members in this course. When we come back on Monday, we are going to do a full-blown analysis problem start to finish. So the idea behind this problem is this. We have a tension member, and we are going to determine the capacity, okay? And the idea is, if you can determine the capacity of this section, the next question you can ask is, how do we determine what member we need to select in order to properly resist these loads? And that is design. That's all I have, everybody. You all have a wonderful weekend. Try and stay warm.